So, I'll turn the time over to David.
Thank you. Good afternoon, everyone. I'd like to thank Weaver for hosting this wonderful conference every year, and thank you for joining my session. Today, I'm going to talk about geothermal district energy systems, and no, that's all. I'd like to. You all get to be my guinea pigs today. This is a new presentation. I've presented on this material to technical architecture and engineering audiences before, and for this presentation, I've tried to remove a lot of the technical distractions and focus really on the core concepts and why we do what we do. So let me know how it goes. To start off, I'd like to kind of reframe the way we think about our energy systems. And most of the energy systems that we all have in our homes and businesses and facilities today, I would characterize as throwaway energy systems. Whether that's burning a fossil fuel to heat, or whether that's using conventional air conditioning technology to reject heat, it's a single pass system. You either heat or you cool, and that energy is gone. What we're going to talk about today offers some options for recovering and reusing that energy. Some of you may be familiar with the basic concepts of a geothermal heat pump system. I gave a presentation here last year on exactly that. I'm going to give some detail about how the systems are designed and constructed. Essentially, you're using native ground temperature as a heat source and heat sink. You can do it anywhere in the country, anywhere in the world, it's a thermal technology. You're heating and cooling buildings, industrial process heat, potentially hot water, etc. It's not electrical generation geothermal, as sometimes people think about, which we also have in this state as a great technology. It's just a distinct technology from what we're talking about today. This is the type of system that I have in my own home. A basic standalone geothermal system where each building or each zone would have its own heat pump and its own ground loop. And that's a great system, it's very efficient, but there are some other options depending on the size of your facility. So what if you have many buildings in close proximity, whether that's a campus or an inner city development, maybe mixed-use development, a mix of, say, maybe retail, residential, etc. You can actually connect those dots and receive many benefits from connecting those energy loads. So, for example, by connecting energy loads, the cost of installing geothermal across multiple buildings connected is significantly lower than it would be if you did a geothermal system for each of those buildings on a standalone basis. And also the energy efficiency, the operational expense of those buildings is lower as well. As the diversity of those loads goes up, so the bigger the mix of time of day, occupancy, architectural mix or use mix of those buildings, the benefits go up, as you'll see later. So the fundamental principle here for how we move energy is using water. Water is a good conductor of heat. And it's very easy to move it around a facility or a campus, sometimes even long distances via pumping. So we use water loops inside individual buildings, and then we also use water loops across campuses to connect buildings. And using heat pumps, we can actually extract energy from that loop, or do heating from a zone's perspective, or put energy in that water loop, or do cooling from a zone's perspective. The key takeaway here is that energy, it's not, as I showed in that first slide, it's not a single pass concept here. We're trying to harvest, treat, and reuse energy. Our basic concept for geothermal district energy system is essentially consists of 4 stages. 3 mandatory and the 4th is optional. The first stage is using water source heat pumps inside each building or zone to share energy within the building, and I'll get to each of these in more detail here following. Then using a central loop that connects multiple buildings around the facility, and then sharing energy between those buildings or among those buildings. And then third, using geothermal bore fields for a heat source or heat sink. If the net energy balance of that central loop starts to get out of the specified range, then we can engage the geothermal bore fields to either absorb some of that excess heat if the loop is getting too hot, or to provide heat if that loop is getting too cold. And then the fourth optional stage is what we call a hybrid component, and that's using one of those conventional energy devices, whether that's a cooling tower or a boiler or potentially some other creative options to deal with extreme peak events. So to get into a little bit more detail, I'm not going to dwell on the vapor compression refrigeration cycle, but if you want, you can Google it. You all live with these devices every day, so this is essentially the same concept as a refrigerator in your kitchen or a conventional air conditioner. The big difference with a geothermal heat pump or a water source heat pump is that instead of absorbing or rejecting heat from air, like most of those devices do, we are absorbing and rejecting heat to or from water, which then gives us the ability to recover it and move it and reuse it. You can see here's a typical diagram of a photo of a water source heat pump installation. You can see, there we go. Right over here is the connection of that heat pump to a building water loop. Okay, so when this unit is in heating mode, heating the air going out through the ductwork, it's actually taking heat out of this building water loop and putting it in the air. And when it's in cooling mode, it's taking heat out of the airstream, cooling the airstream by removing that heat and delivering it to the building water loop. So in the next room down, if this unit's in heating and the next one down is in cooling, you can actually just move that heat from one unit to the next. That ability to recover and move heat presents a lot of opportunities. All of a sudden, all of these things that engineers typically consider to be loads, that we have to deal with in some way, can actually become an energy resource. So, whether that's computers, equipment, lighting, people, human bodies, 250, 300 BTUs an hour. So all of these things, solar gains, all of these loads that typically just become a liability that we have to get rid of, become a resource. And the question is, okay, well, how do we capture that using the heat pumps? And then where can we reuse it? This is a conceptual diagram of an individual building with a water source heat pump loop with a diverse load. So say, for example, a typical spring or fall day, you may have the south side of a building requiring air conditioning, while simultaneously the north side of the building requires heating. And in most buildings today, that requires the simultaneous operation of two separate systems. The heating system and the cooling system. The heating system is going to be combustion based, right? So you're burning something and sending waste heat out the stack. And simultaneously, your air conditioning, taking heat out of zones in a building and rejecting it to the outside air. And what we're doing with this system, with a water loop and a pump, is recovering heat from the zones that are in cooling mode, the blue ones there, and delivering it to the zones that are in heating mode. So that represents a tremendous number of the hours of the year, potentially up to 90% of the operational hours of the year. There could be some form of energy sharing back and forth, even just within an individual building. Now, of course, if the building itself is truly at peak conditions during, say, a cold spell, blizzard, then all the units might be in heating and there's no opportunity for that energy sharing. Likewise, if the individual building is at peak cooling conditions, there's no opportunity for sharing. All the units are in cooling. And typically, that would be dealt with either by going to the individual building's geothermal loop, if applicable, or potentially a boiler or cooling tower. Now, when we start looking at a geothermal district energy system and we have that piping in place to connect multiple buildings, before we go to the geothermal system or the conventional energy equipment, we can actually engage those pumps on the central loop and circulate fluid from building to building around a campus through buried pipelines and recover that heat. And what you find is that just like individual zones, I mentioned, that classic example of south side of the building's in air conditioning mode, north side of the building's in heating mode, or the core of the building is in heating mode. You'll find that with diversity across the campus, many times you have certain buildings that are cooling dominant and other buildings are heating dominant. So in general, your commercial spaces are going to be cooling dominant because of higher occupancy, probably higher solar gains, etc. Residential areas are likely to be heating dominant, at least in our climate. And so by connecting these buildings, you expand that ability to take advantage of system diversity and recover energy on a building by building basis, the same way that many systems in place already do, zone by zone. So, diversity is a good thing from a thermal perspective, and whether that's a mix of use, mix of occupancy schedule, we can start to think about other opportunities to tie in different loads, domestic water. So if you have a high cooling requirement, you could think about placing that heat into your domestic water system, and again, offsetting or eliminating combustion for domestic water. For example, I like to think about pairing up some of these resources. Maybe a data center and an aquatic center, they have complementary energy needs, so you can cool the data center with that energy in the swimming pool. Commercial kitchens, domestic water heating, those are things where you actually have simultaneous diversity, not just diversity over time. Stage 3, if the central water loop starts to get out of its temperature range, then we start to engage pumps and circulate water through the buried heat exchanger piping. And in the summer, then that means that we're rejecting heat to the ground, cooling the building, putting heat to the ground. In the winter, that means that we're absorbing heat from the ground and bringing it into the buildings. And I'll show you just a couple pictures for people that aren't familiar with the technology. Here you can see a typical drilling rig installing a geothermal ground loop. This is the loop here, this black pipe, high density polyethylene, and a large commercial system. My home has 2 of those loops in the front yard. A large commercial system might have hundreds. There are also other ways to connect to the ground loop using ponds, water wells, lots of other options that I won't get into in detail here. This is the most common. And then multiple boreholes here are shown headed together in a trench prior to being buried. So essentially, the key thing to understand about the ground loop is that it's just a buried heat exchanger. That's all it is. We're circulating fluid through closed circuit pipe to the ground and using that to dissipate or absorb heat. And it has a thermal battery or a thermal buffer, maybe a capacitor, thermal capacitor would be the best way to think of it, both short-term and long-term. So if you think about a peak cooling demand, the ground can spread that over time, and by doing so, reduce the electrical demand on the building, maintain comfort much more efficiently, etc. Stage 4, and this is the optional stage, you can choose, driven by either space constraints or economic constraints, to design a smaller geothermal system that still provides most of the benefit. So the typical rule of thumb is that about half of the geothermal bore field capacity, if you think in terms of air conditioning tons or such, can cover about 90% of the annual load hours that would be required if you could install 100% capacity. So what that means is that especially with the diversity of a campus system, you can radically reduce the first cost of the system while still providing 90% plus of the cost savings through operational expense and the environmental benefit of the system. Oh, and it's worth mentioning, in some of our retrofit applications, we've been able to use existing boilers or cooling towers on some of these systems. So there was no added expense to add the hybrid component. And if they were partway through their service life, because now they're only running maybe 5 or 10% of the hours of the year, instead of thousands of hours per year, then the life of that existing equipment has been extended pretty dramatically. Just quickly, a couple of other ideas. Once you have a central water loop, that becomes an energy highway for all sorts of things. If you have solar hot water collectors, those can be tied in so that isn't just used for domestic water production, but if the domestic water tank is already hot, you can put that energy in the system and pull it out someplace else for another purpose. fountains can become a viable heat rejection device. That's in use in several places. And this is one that we always like, but it's a gray water heat exchanger that is essentially replaces a section of sewer pipe on a project in downtown Salt Lake City and recovers waste heat from the sewer. So again, all of these resources can be connected together, and the end result is greater than the sum of the parts individually. So putting these stages together in terms of actual system operation, stage one again is sharing energy within the building, zone by zone. And this is all controlled on temperature, by the way. So as long as the building is operating within, that loop is operating within a temperature band that the heat pumps like, they can be in heating or cooling mode at any time, and that building just circulates happily on its own. As soon as the building, or a building, starts to get out of that temperature band, then we engage pumps to and from the central water loop to moderate that building water temperature. Okay? And in this case, you can see there's one building in heating, one building in cooling, so we're just moving energy from one to the other. If the campus as a whole, if the system as a whole becomes heating dominant or cooling dominant at any time, then we start to engage the geothermal ground loop and store that heat. If we're in cooling mode, we're storing that heat for later use. If we're in heating mode, we're pulling heat out of the ground. And then if we've got a hybrid component, and if we start to get out of our prescribed temperature range using just the geothermal, then we can pull in a conventional piece of energy to deal with a peak event. Okay, the reason that all this works so well has to do with the distribution of temperature over the course of the year. This is data showing if you took all of the hours of the year, recorded the temperature, and then sorted those hours by temperature band. This is a graph of what that would look like. How many hours per year is at each temperature range in Salt Lake City? And what you can see there is that we've got a huge portion of the central that central part of the graph there, where 90% of the year, where we can share energy from zone to zone within a building, or even better, that range is expanded if we've got a district system, share energy across a campus, and a very few number of hours per year where we truly need the peak capacity. And that's where that hybrid component comes in. And of course, mechanical systems need to be able to provide for comfort during those peak events. But the flip side of that is that historically most mechanical systems have been designed for peaks, and they haven't been designed or optimized for the actual operation that they see for 90% of the time. And of course, the effect of that is a loss of efficiency for most of the year. So that's now I'd like to share a couple of examples from real-world projects. Colorado Mesa University is an institution, I think, similar in size and mission to Weber State. It's in Grand Junction, Colorado, and this is an institution that just went through a rapid growth phase. 2006, they had 3,500 students. 2014, 9,500 students. The size of the campus has roughly doubled. As part of this building spree back in 2006, our firm was engaged to design a standalone, typical commercial geothermal system for one new classroom building. Partway through that design phase, they mentioned that they were planning to build another new building across the street, and asked us to analyze that. And we said, well, the street's torn up. Let's put a pipeline in place and connect them. And the system grew from that point on the basis of its performance. They added more and more buildings, and now at this point they've got 13 buildings connected to this district system, able to share energy back and forth, and they're continuing to build more. We're in the process right now of adding 2 new dormitories in the aquatic center. Essentially, our vision was for a modular approach, so the system could grow with the institution and function at each stage of completion completely independently. So rather than having a typical central plant where you've got one large mechanical plant that serves the entire campus, we have distributed mechanical rooms. So each phase of campus expansion, one of the buildings was designated to have a mechanical system to pump that portion of the loop. And as a result, each wing of this system can be operated independently or isolated and operated independently if required for some reason. If someone went crazy with a backhoe or something like that. You can see they're installing the 18-inch central circulating loop there in the picture with the man standing in the trench. Current scope there, as I mentioned, we've got 13 buildings currently tied together. It's about 1.2 right now. By midsummer or end of summer, it'll be more like 1.5 million total square feet integrated tied into this system. This is probably the second or third largest geothermal system in the United States at this point. The largest being Ball State University in Indiana, which is also, it's a very similar district energy system. A little bit different technically, but same concept. And if any of you have experience with geothermal, you may notice that 153,000 feet of bore field, it sounds like a lot if you don't have experience with geothermal, but to do a 1.2 million square feet of service, or 4,000 tons of service with 153,000 feet of borehole is kind of a ridiculously small amount of borehole. And the reason for that is because the system is so diverse that the majority of the energy that's delivered by this system is recovered and coming from other buildings. It's actually not coming from the ground. The geothermal has become, in a sense, an auxiliary to this system, and the primary functionality of the system is just moving energy from building to building. There are hybrid components here. Fluid coolers do run during the peak summer months, occasionally. The boilers in the last 2 years have actually not had to run. So that's maybe we've over-designed it on that side. It was intended to use the boilers occasionally, and as the energy is balanced out, it, at least as of now, hasn't been necessary. The central loop installation cost about $1 million, a little bit over, probably 1.2 million, and they're experiencing about $500,000 a year in energy savings, and they also received significant carbon credits from the state of Colorado. This is a snapshot of the main dashboard for the central loop. You can see that yellow pipe in the middle is the main section of the central loop, and there are various wings. Looks pretty complicated on here. The thing I'd like to point out is that you can see, so each of these are buildings, and you can see that each of them is pumped or connected primary, secondary to the main building, or to the main loop rather. Each of these is a geothermal bore field, so they're all pumped individually. Basically what happens is this central loop is circulated on variable speed pumps, and as necessary, controlled on temperature, each of the loads and each of the energy resources can be ramped up or ramped down as required. So it's a central loop, but the control, it is centralized in that it communicates with each other, but each component of the system operates on a standalone kind of on-off basis, or modulating basis, I should say. It's not that the whole system is on or off. Individual pieces of the system can turn on or turn off, or ramp up or ramp down as necessary. And this is an interesting feature right here as well. Built into the control strategy here, we specified a global demand limit, where with a single button, the facilities team can do a global setback, temperature setback, and temporarily reduce the peak kilowatt demand of the entire campus HVAC system. And they get paid, I believe it's $10,000 per incident by the utility, because this university is the largest power consumer in their grid. When they are about to experience a brownout condition, the utility calls up, they click that button. So at this particular system, as I mentioned, the boilers have not had to fire. About 89% of the energy in the system is coming from either energy recovery from building to building or from the geothermal system. The balance coming from the fluid coolers. Another example, a little bit closer to home, a little bit smaller example, but same concept, is Uinta Basin Medical Center in Roosevelt, Utah. Some of you may know it. It's pushing 160,000 square feet currently connected. The current system consists of 2 medical office buildings, the first of which was built again as a standalone geothermal system in 2001. And the community system has been master planned and implemented step by step since that time. And a nursing home, intensive care rehab facility, and then the main hospital building has now been connected and is about 20%. They're going through a kind of a wing by wing retrofit to use heat pumps and connect to this district energy system. About 20% of the square footage is currently connected. The neat thing is they anticipate that they'll be able to connect about 75% of the square footage of the hospital before they have to drill any more loop fields based on the diversity of the system. So it's, again, performing better than, we as engineers are conservative by nature. And when the system gets into operation, we discover that it's performing better than design due to the diversity. They're able to add additional square footage without adding any of the expensive drilling, which is pretty cool. 12-inch central loop, the other one, Mesa State, was a mix of 18 and 12-inch central loop piping. You can see here's a layout of the campus. The yellow are the areas where they've done geothermal borehole drilling. You can see there's the main hospital here, the first office building, mode 1 here, medical office building number 2 over here, and the villa is the care and rehab facility. This is operational data from the medical center showing what happened to the system as they added new buildings and added diversity to that system. You can see the blue, the main hospital building in 2010 was not geothermal, and you can see that the gradual reduction there as they've started to implement that retrofit. You can see now they're maybe 20% geothermal. The red, the green, and the purple are all 100% geothermal, and the blue, the dialysis building, is not geothermal. So you can see it's 24 hours and the villa is 24 hours. You can see the difference there. Even for a 24-hour facility, this is dollars per square foot per month on average for the last several years. Another interesting example is what's going on in Vancouver, British Columbia. They're actually working to apply this strategy to inner city developments, and they've developed a special drilling technology that allows them to drill through the floor of an operational parking garage. So they can go into a building that's occupied, take out like 5 parking stalls at a time, and punch their hole through the floor, connect all of that, and actually run piping using horizontal drilling, similar to what you'd see for fiber optics installation, and connect buildings across the street in inner city. And it's the same concept, some specialized technology. I think this is a really exciting thing because most of what we've done so far has been places like college campuses and military bases, et cetera, that actually have some land to work with. And this solves one of those problems for large-scale inner-city applications. I think one of the big takeaways is that this is exciting stuff. This is from a design standpoint, cutting edge. And some of these first generation of systems are getting to the point now where they've got enough operational history to really prove the concept. I think in many cases the challenge is not a technology challenge anymore. It's a finance and a business model challenge. And the biggest place where that's the case is for applications where you may not have, where the owner may not be the one paying the utility bills. So like a tenant-owner relationship or something of that nature. So coming up with business plans that where you can actually meter and sell BTUs. The technology is there to do that. There are some cases where people have got successful businesses built around that strategy, but I think there's a lot of opportunity in that. If any of you are business people, there are opportunities there, and it continues to spread. We're currently working on a system at another educational institution here in Utah, where the first piece of we did a standalone building again about a year and a half ago, and they're doing 2 more buildings this summer, and we're looking at connecting those with the first component of a district energy system, kind of on a 20-year plan. And I'm pleased to say Weber State is also an innovator in this realm. Our company, in working for Weber, is currently working on a feasibility study for looking at a system like this here on campus. We drove 3 test holes in some of the parking lots to the north, so if you're students here, you may have seen a drill rig back in November, December, wondered what on earth was going on, and that was it. So I think with that, I'm probably out of time. Maybe I don't know if you have time for a question or two.
Can
So ground source heat pumps do require electricity, and they have fans, circulating pumps, compressors, etc. I think one thing that may surprise people, if they didn't think of it before, is that because you're using electricity to run those components, even in the winter, your electricity bill in the winter will go up, but your electricity bill even in the winter should be less than what you were previously paying for gas or propane or whatever the other fuel would be. So your net annual kilowatt hours may increase, but your net annual energy will decrease, both in terms of dollars and in terms of what you convert kilowatt hours to BTUs or vice versa. The other case where you may have some issues there, and this is mostly on the residential side rather than the commercial side, but a lot of residential systems you can use electric resistance heat for backup or emergency heat, and just like any mechanical system, if it's not installed and controlled properly, I have seen a case or two where the electric heat was wired such that it overrode the heat pump. So at that point, it's basically a toaster. But yeah, so is it possible? Yes. Is it normal that that would be an issue? No. So the question that so you said you're a student at University of Utah. Utah State. Okay. So and that's a common system. So you said that their campus system is a central system using steam. They've got the steam tunnels and the infrastructure and piping and stuff in place. The fundamental difference between this type of system I described today and a central plant, either steam or chilled water system, probably both, is that we're not. The central system in this case is not delivering a specific temperature. Okay, we're specifying a temperature range. We're saying, we don't want it to get colder than maybe 45 or 50. We don't want it to get hotter than 85 or 90, because that's a range in which heat pump efficiency is very good. And so we engage these resources like geothermal or even the boiler or cooling tower if necessary to maintain the loop within that operating parameter. Whereas a steam plant or a chilled water plant has a specific temperature that you deliver to the points of use, because they're using devices like fan coils or VAPs or radiators that require a specific temperature. So there are ways to gradually transition from a steam or chilled water system, and that's one of the things that we're looking at Weaver State. One of the design challenges here for sure is taking an existing central plant system and transitioning it. If you could flip a switch, it would be a lot easier, but to transition it so that all the components continue to work through that, potentially decade-long or longer transition is the challenge. And there are ways to do it. That's at Ball State, the biggest system that I mentioned, has done that. They were a steam plant, typical old school steam plant, and that's part of what they work on. There's one more question I think.
Yeah, some guidance that would dial back or ramp up any more temperature setting. Comment on that and what that does.
Yeah. So the question was, he said he heard some guidance that with ground source heat pump systems, that you don't want to use thermostat setbacks. And I think in a general sense that's true. In my house, and this is talking about a standalone geothermal system again, but I don't use setback at my house unless I'm going on vacation for like more than 2 weeks, which doesn't happen as often as I'd like. So the thought process there is that most conventional heating and cooling systems are vastly oversized, and so there's not a huge penalty. If you have the furnace I took out of my house was 70,000 something BTUs per hour, and I put a 3-ton or 36,000 BTU an hour heat pump in, and I did the load calculation myself, and it works beautifully. So my furnace was twice as large as it needed to be, which means that if you have it set back radically, you flip a switch, and it ramps up very quickly in short cycles. Okay, the geosystems are sized much more specifically to the load at hand, and so there's not as much leeway for a rapid recovery, basically. And by doing that, you draw down the temperature and take an efficiency penalty. See me afterwards if you want to know more about that. I've got cards up here on the table if anybody wants them, or if you have questions, feel free to shoot me an email.